This is an overview of the infinite spongy universe model of the cosmology of the universe. The ISU model is divided into two major realms, the micro realm and the macro realm. The most significant feature of this model is the striking sameness in the mechanics taking place in the two realms. At the micro end, tiny quantum waves converge within particles to form multiple high-density spots within the particle space. At the macro end, two or more Big Bang arena waves converge to form big crunches that collapse bang into the landscape of the greater universe. The high-density spots expand into new quantum waves, and the Big Bangs expand into new Big Bang arena waves. The high-density spots and the crunches are quantum amounts of energy in their respective realms, and at the opposite ends of nature's energy increment scale. This is a depiction of the quantum amounts of energy that lie at the opposite ends of the energy increment scale. At the tiny end of the scale, particles are composed of tiny quantum increments, momentary high-density spots that form at the overlap of quantum waves within a particle. At the large end of the scale, nature's largest energy increments are big crunches and their corresponding Big Bangs that come from the overlap of two or more parent Big Bang arena waves. This video looks toward the infinite and addresses the macro realm of the ISU model. It features our Big Bang, its preconditions, and the arena of space it encompasses as it expands. It describes the multiple arena landscape of the greater universe where big crunches form and collapse bang as a process called arena action takes place there. The key result of arena action is the defeat of entropy on a grand scale. High entropy parent arenas converge, allowing new low entropy arenas to form and emerge and fill with galaxies as they mature. Galaxies host stars, and stars host hospitable planets on which the generation and evolution of life naturally occurs. Life is prevalent throughout the billions of galaxies that form in each maturing arena. The infinite arena landscape is populated with those life-hosting arenas, and as arenas form and play out, life flourishes throughout the entire universe. This slide depicts various sized arenas populating a segment of the greater universe. The cutout box shows that our finite expanding Big Bang arena is filled with galaxies, just like all maturing arenas are filling with galaxies as they expand. An arena is an open system within the greater universe, meaning that as an arena expands, matter and energy can freely enter its space. Why say the universe is spongy? Though the ISU is infinite and not expanding as a whole, local Big Bang arenas expand, and when they intersect and overlap, their galactic material gravitationally collapses to form big crunches, which in turn collapse bang into new expanding arenas. It is a spongy kind of action. Are the physics the same in each Big Bang arena? Yes, there is just one universe, and the physics are the same everywhere. Each new expanding Big Bang arena is preceded by two or more similar parent arenas, each with the same physics. Don't confuse the ISU with the many worlds interpretation of quantum mechanics or with string theory, where there are multiple universes, each with their own unique set of physics. In the ISU, there is one set of invariant natural laws and a sameness of the physics in every Big Bang arena and throughout the ever-changing corridors of space that separate them. This slide is about the beginning. Some models of cosmology fail to address the beginning, but logically there are three major explanations for the existence of the universe. They are depicted on the sides of the triangle of cosmological explanations, with the imperative, pick one. In the ISU model, there was no beginning, and it is built on the premise that the universe has always existed. This slide is about time. By choosing always existed from the triangle of cosmological explanations, the time continuum of the ISU is derived as depicted in this slide. Time is infinite and has no beginning and no end. The timeline is a continuum of nows, with each point in time representing a now on the continuum as time simply passes. Given a universe that has always existed, with its infinite time continuum, it is axiomatic in the ISU that space is infinite too. This model accommodates a perpetual sameness, a homogeneous and isotropic Big Bang arena landscape on a grand scale, where the spongy action of Big Bang arenas has always been playing out across the greater universe. That premise of sameness and perpetual arena action includes the hypothesis that life has always existed in various renditions of high evolution, here and there across the infinite universe. The ISU model features the presence of life right along with and as part of the infinite and dynamic Big Bang arena landscape. It is a common concept of modern cosmology and most related models of the universe that the universe is finite, bounded, and closed thermodynamically. The laws of thermodynamics say that entropy continually increases in a closed system, meaning that the useful energy in a closed universe gets used up, and the system eventually reaches the point where life cannot be supported, let alone generated or evolved. The heat death of the universe is called. The ISU defeats entropy and accommodates life perpetually on planets here and there, in galaxies and arenas, across the landscape of the greater universe. It is an infinite universe that features Big Bang arena action to continually provide new low-entropy arenas out of old, greatly expanded and cooling arenas. It is the quintessential open system. The mechanics of the defeat of entropy are depicted in the following images, starting with ongoing expansion of two or more parent arenas and the depiction of a big crunch forming where they overlap. The premise is that where two mature, galaxy-filled Big Bang arenas that have been expanding towards each other over billions of years eventually intersect and overlap, creating a shared space where their respective galaxies converge under the increasing force of gravity as the distances between them decrease. There is a long period of convergence, characterized by a swirling rendezvous of matter and energy contributed by each parent arena. A gravitational accumulation of galactic material forms a big crunch at the center of gravity in the overlap space. And when a big crunch reaches critical capacity, it will collapse bang into a new low-entropy expanding arena. As each new arena matures, it fills with stars and galaxies that will provide hospitable planets where new life will be generated and evolved. Each finite new expanding arena is characterized by a sameness in terms of its physics. The natural laws that were in effect in the parent arenas are maintained and are in effect as each arena follows a natural process of maturity. A hot, dense energy ball typifies each Big Bang event, and as that initial energy expands, it is demonstrating one of the two major forces present in the ISU, a force called energy density equalization. The extreme high density of the hot Big Bang energy ball immediately expands to equalize with the much lower energy density of the surrounding space, and a rapid period of expansion of the finite energy ball takes place. During that rapid expansion, particles form out of the wave energy of the hot, dense Big Bang ball of energy and are imparted with separation momentum. As a result, as they form, particles are moving away from each other across the entire arena. In close quarters, gravity is strong enough to cause clumping, and as clumps accumulate, they conserve the separation momentum that was initially imparted to their constituent particles. Nevertheless, expansion momentum is stronger than gravity as the distances increase, and the inverse square law takes effect. Separation momentum is conserved throughout the maturing process, and ultimately, the galaxies and galaxy groups that form and fill each maturing arena inherit separation momentum as well. Distant galaxies are observed to be moving away faster and faster. We have gathered data from the light spectrums of galaxies throughout our Hubble view, and the Hubble redshift, the shift of the spectral lines towards the red end of the spectrum, has allowed for the quantification of the rate of separation. Certain types of cosmic events, like variable stars and supernovae, also provide us standard candles or markers with known magnitudes that can be compared to their visible magnitudes. And they have given us evidence of the increasing rate of expansion of the universe, a dark energy. Dark energy is explained in the ISU as the effect of separation momentum winning out in the battle of forces between energy density equalization and gravity, as our high-density arena expands into the lower density surrounding space, and as the inverse square law lessens the opposing force of gravity. At least dark energy wins out until the arena expands and overlaps with a nearby arena, at which time separation momentum is interrupted for large portions of the galaxies that are caught up in the overlap space. In the ISU model, the greater universe is characterized by a cosmic microwave background, maintained by arena action throughout space and across the continuum of time. Our Big Bang arena has its own CMB, composed of the pre-existing background in the surrounding space and individualized by the specific preconditions present. The individual backgrounds of our parent arenas, which varied based on their relative ages when they converged. Our CMB is characterized by some interesting anomalies. There is the wide-angle temperature difference, called hemispherical asymmetry, or dipole anisotropy, and there is also an interesting cold spot. When you look at the temperatures of that background on angles wider than 30 degrees, asymmetry in the background temperatures is detected. There is a meaningful directional difference in both the quadrupole and dipole angles of measurement. Can the hemispherical asymmetry be explained simply by the peculiar motion of our local group of galaxies relative to the CMB rest frame and driven by some great attractor? Evidence has not yet borne out that hypothesis. Is there some other explanation not yet determined, like errors in masking out stars and galaxies and even dust clouds? Understanding the CMB data is one of the interesting fields of investigation going on today in the cosmological community. Future mapping of the CMB with more accurate instruments and better masking techniques will certainly be forthcoming. Also yet to be explained is the cosmic cold spot that appears in both the YMAP and Planck CMB sky surveys. Is it some dark flow that signifies a close connection with some other cosmic structure? Is it an outflowing plasma jet typical of some versions of a black hole, but on a massively larger scale? Or is it the start of our own arena overlap that will lead to a new Big Bang arena that will someday reoccupy and repopulate our current location in space? There are many questions, and though the ISU model is designed to be internally consistent and not inconsistent with scientific observations and data, there is much that is yet unknown. Think about the cosmic microwave background that our arena is expanding into. It is coming from all directions in every Big Bang arena in the ISU model. And it fills all space between arenas as well. In this model, the temperature differences discovered in our CMB mapping are taken as possible evidence of arena action playing out across the landscape of the greater universe, and of recent CMB variations in the histories of our individual parent arenas, which then in turn directly affected our own arena by imprinting it with the anomalies of asymmetry and the cold spot. Given that entropy is being defeated every time a new arena forms out of the remnants of its parent arenas, the greater universe is continually populated and repopulated with various highly evolved life forms with survival instincts. Over an infinite history of the generation and evolution of life, this model predicts there are successful life forms that have overcome the calamities of their fragile planets and even the finite lives of their home stars to achieve lengthy heritages marked by the accumulation of vast amounts of knowledge and highly advanced technologies. Perhaps we humans will become one of those intelligent life forms that learns to survive and escape our planet and solar system and spread throughout our galaxy and beyond. And who knows what or who we will meet out there.